This module provides an introduction to limits. In section 2.1, we're going to see a preview of calculus and talk about the two main problems that we have. One is the tangent line problem, and the other is the area problem. In 2.2, we'll talk about the limit of a function. We'll do this by building up an intuitive approach through graphical and numerical analysis. And in 2.3, we will learn about the limit laws, which provide for algebraic manipulations of determining limits of a function. So the two main questions that calculus addresses is, one, the tangent line problem. How is it that we determine the slope of a line tangent to a curve at a single point? And the single point here is the crux of the problem. Recall this: to determine the equation of a line, we must know the slope of that line. But determining slope requires 2 points and not just a single point. So the calculus will address how we can find the slope at a single point. The other part of the problem is the area problem, and it's how do we determine area under a curve. If we were given simple polygons, triangles, squares, rectangles, trapezoids, or even a circle, we know from geometry, we know those formulas about how to find the area of those shapes. The problem becomes when the area is under a curve. Now, the method of exhaustion is the historical origins of the limit. And when early mathematicians were working on solving the tangent line and the area problem, they used methods, initial work on the area and the tangent line problem used methods that approximated solutions. And the early mathematicians, we're talking in ancient times in Archimedes, they developed a method called the method of exhaustion. It is the precursor to the limit. And what they were looking at was how do we find the area of a circle. Okay. So this idea of a limit and area has been worked on for thousands of years, and it isn't until the late 19th century that we get the formal definition of a limit that we know today and that you'll learn in this class. So when we start talking about limits, we're going to take the same approach our mathematical ancestors did, and we're going to look at a formal, not the formal definition first, we're going to look at an intuitive approach. So below, in the figure below, you can see 3 black circles, and Archimedes was working on trying to determine the area of a circle. Okay. So one approach said, let's put a polygon inside of the circle. And it was well known how to find the area of a polygon. So this area here could be calculated very easily. And this was an approximate method because you can see then that there is some extra area to the circle that is left out of that approximation. But then the thought was, well, let's, continuing with the inside approach, let us just increase the number of sides to the polygon and find the area of that polygon. So when we find the area of the red polygon inside of here, then the amount of underestimation, the amount of area that's left over, is less than the original estimation. And it just continues to get better as the number of sides of this polygon increased. The remaining amount outside became less and less, and the under approximation became more accurate. Now that's just one approach. I mean, we didn't have to put the polygon inside. We could have made the polygon on the outside of the circle, in which case the approximation that was obtained was an over approximation. So it was the approximation of the circle plus a little bit more. But again, as we increased the number of sides to that polygon, the amount of overestimation of the area decreased. And as you continue and getting more and more sides to these polygons, both the under approximation and the over approximation of the area of the circle became more and more accurate. So using that idea of geometry and the method of exhaustion in a limiting process, over time we were able to discuss the behavior of graphs using limits. Okay? So below are 3 graphs, and let's make note that the graphs for each of these functions, the domain does not include x equals 2. And that allows us then to ask about what is this behavior of the graphs around x equals 2. Okay. So in our first graph, you can see that as we go, here's 2. Okay. As x is at 2, it just really takes a little bit of a skip there. But in our second function, there's a bit of a jump. And in our third function, remember there's a vertical asymptote here at x equals to 2. And it's impossible to get from the right-hand side to the left-hand side, okay, because there's the barrier of the vertical asymptote. Right? So 3 different behaviors. We can talk about them in terms of limits. So let's define a formal, well, not a formal, an intuitive definition of the limit. Okay. So we're going to let f of x be a function. It needs to be defined at all values on an open interval, and we'll see why that is later. That open interval needs to continue a. That is, we're trying to find the limit at x equal to a, with the possible exception of at a itself. Okay, so let's just take a second for that. That is the first case here. Here, at x equals to a, the function is not defined. However, the function values all the way around that in an area around x equal to a, which in our case is x equal to 2, are defined. So we let f of x be a function defined at all values on the open interval containing a, with the possible exception of at x equal to a itself, and then we'll let L be a real number. Okay. Now, if all of the function values approach this real number L as x approaches a, okay, and it doesn't have to be that x equals a, but as x approaches a, then we will say that the limit of f of x as x approaches a is L. Now, saying that a little bit more succinctly is as x gets closer to a, f of x gets closer and stays close to L. Okay. And symbolically we can write this. This is the limit as x approaches a of f of x is equal to L. This is our notation, and we should note that this is a full limit. Because there are other types of limits. It isn't just the full limit. So for example, we have things called one-sided limits, infinite limits, and then there's a relationship between those and vertical asymptotes. So let us look here. Okay. In our first function, here is x equals to 2. Okay. So I could look at a one-sided limit. That is, let's say I want to look at the limit as x approaches 2 from the left-hand side. That is, if I'm coming this direction, and I take those values of x and I put them into our function f of x, what's happening with them? Well, the function values are headed up and they're approaching this value here of 4. So we can say the limit as x approaches 2 from the left of f of x is equal to 4. And we can do it from the other direction too. What happens as the values of x approach 2 from the right? So this would say the limit as x approaches 2 from the right of f of x. Well, if you look what's happening to the function values in that case, they are also approaching 4. And here, the limits from the left and the limits from the right agree, and then we can say that the full limit, the limit as x approaches 2 of f of x, exists, and it is equal to 4. Let's do the same analysis in the second graph. So here's x equals to 2, And let's see what's happening with the limit as x approaches 2 from the left of our function, and our function now is g of x. Well, so as x is approaching 2 from the right, what's happening to the function value? Well, the function value is staying constant, or that's constant, and y is equal to negative 1. As opposed to if we look at what's happening as x approaches 2 from the right of our function g of x, they're approaching this direction, and that is equal to 1. In this case, the limits from the left and the limits from the right do not agree, and so the full limit, the limit as x approaches 2 of g of x, well, it does not exist. We abbreviate that DNE, does not exist. Lastly, remember we have a vertical asymptote here at x equals 2. So let's ask the same questions. What's happening to the limit as x approaches 2 from the left of our function, which is h of x? What's happening as we come this direction to the function values? Well, the function values are taking off to positive infinity. Now, note that we write that it is equal to positive infinity, but note, positive infinity is a concept and not a real number. So this is an instance where the limit does not exist, because remember, L needs to be a real number, but we just write that it's equal to positive infinity to make the notation that it is taking off in one direction. It could also be taking off to negative infinity. Neither one of those limits exist, but we make the notation of positive infinity or negative infinity. And again, we could do it from the right. So again, we could say the limit as x approaches 2 from the right of our function h of x. This also takes off to positive infinity. Okay. So these limits do not exist, but we make the notation of positive infinity. And if a function approaches either from the left-hand limit, a right-hand limit, or from the full limit, if we can write that that's either positive or negative infinity, this is the definition of a vertical asymptote. In the last section, we're going to talk about the limit laws, and they will allow us to algebraically evaluate limits. That means we'll get to use the equation. Okay, just put our pencil to the paper and do some calculations. So the two basic limit results are this, is let's say f of x is equal to just our basic function x. Right? If you want to take the limit of that function as x approaches a, okay, so I could have written f of x in there, but you can also just directly write in what the function is, and that's very helpful when we're doing direct substitution. We can say the limit as x approaches a, well, we'll directly substitute a in for wherever we see an x, and that gets us just to a. So that's our first result. We should also note, what if we had f of x being equal to a constant function? So this is just a horizontal line where y is equal to some constant, say 5. Okay. Well, if we're going to take the limit of that as x approaches a of that constant function, so I could write f of x, but I'll just write in what the function, the explicit equation of it. Notice now that there is no place, there's no x in here. So there's no place to let x approach. So what we have then is the limit of a constant function is just the constant function, as we saw earlier. Okay. So these are our two basic results, and then we can build up from there the limit laws. Okay. So here's a summary of the limit laws that you're going to learn about through your reading and your examples and as you do your homework. There are limit laws for the sums, the differences, the constant multiples, the products, the quotients, the power, and the root law, because these are really, roots really are just powers. You'll learn about these, and I recommend that you put these on note cards, because we're going to be building up a toolbox for you to be able to approach calculus. So if you put these on your flashcards, it'll help you solidify your understanding of what should happen and how we can algebraically manipulate limits. Then you would think that that would be enough, the limit laws. Unfortunately, they are not enough. Like, we can't work with even our very basic trigonometric functions with those limit laws. We need something that's called the squeeze theorem. And not surprisingly, so we use this with the trig functions, and we can use it with any, but the trig functions are important here. The theorem tells us that we can squeeze a function with a limit that's unknown at a point x equals a. Okay. If we can squeeze that between two functions having a common known limit at x equals a, then we'll be able to make the we will be able to calculate the unknown limit. Okay, so let's look at this. So here we have some function. Let's say this is h of x. Okay. And that limit is known at x equal to a. Okay, right here. All right. So we could write that the limit as x approaches a of h of x is equal to that limit. Right? That is known. Now we have another function. Here's another function. This is f of x. Notice all the values of f of x are less than h of x. Okay? But this limit is also known as x approaches a of f of x. And not only is it known, we should really be careful here and look at this. The limit is known, and it's also equal to the same limit that h of x has. Okay, so these two are equal. And then we can put inside of them another function with an unknown limit. If we can do that, we'll call this g of x. So right now the limit as x approaches a of g of x is unknown. Okay. And then we're going to use h of x limit and f of x limit to determine. Okay, so here's the form, that's the intuition, and now let's do the formal theorem. So we're going to let f, g, and h be defined for all, and remember, we don't have to have x equal to a defined on that open interval containing a. So this is our this one's our lower function. This is the middle function that's going to get squeezed with the unknown limit, and this is the upper. Okay. Then remember that the limit of the lower function has to be equal to L, and that has to be the same exact limit as the upper function. And if that's the case, then we can squeeze our middle function with the unknown limit. We can squeeze it between those two and say then that it must also have the same limit. And that leads to two important results from trig. Now notice if we tried to eliminate, to find the limit as theta goes to 0 of sine of theta divided by theta, a direct substitution here would give us undefined. Okay. And the same would happen if we looked at this other limit. The limit as theta approaches 0 of 1 minus cosine of theta over theta. This would also be undefined. So as you work through your examples in the book, they'll show you exactly how this came out, but two important results are that the limit as theta approaches 0 of the sine of theta over theta is equal to 1, and the limit as theta approaches 0 of 1 minus the cosine of theta divided by theta is equal to 0. So these are two that are worth keeping in mind as you progress through the course. All right, so that's your overview for Module 1 and what you'll be studying this week.